Okay, so the first speaker for today is Nicolas Blanco, and he will talk about bifibrations of polycategories and classical linear logic.
Okay, thank you, Christina, for the introduction. And let me just share my screen. Okay, let me just use this opportunity to thank all the organizer of FCT. It's a really nice conference, and I'm happy to be presenting in it. And so today I will present to you a bifibration of polycategories and their relation to classical. So this is joint work with Noam Zeilberger. And this is something that we presented and submitted at MFPS. So you can find, oh, sorry, it's not the, just so that it's not the right thing that is sharing. Yeah. Okay, and yeah, this has been presented at MFPS, and you can find the paper at this address, and you can find more material also on my website. And so before going into classical linear logic, let me just talk to you about compact class categories, so something that most of you should be familiar with, and another way of presenting them, which is by saying that a compact class category is a monadal category that comes with a monadal duality in such a way. So it's a duality between your monadal category and its opposite category. And so in particular, what you have is that if you take the dual of a tensor project, you will get the tensor of the dual. And if you take the dual of the unit, you will get back the unit. And you could rewrite this first equation by saying that the tensor of A and B is the same as the dual of the tensor of the duals. And so when you look at that, it looks a little like a De Morgan law that relates conjunction and disjunction using a negation. And in fact, compact class category can be used to model logic, but where you have both connective, the conjunction and the disjunction, that are interpreted by the tensor. And one way to think of Stautomus category is to actually try to separate these two connective. And so to ask for a category that has two monadal structure, that we'll call tensor and par, that are related by a monadal duality. And so those provide a model for multiplicative linear logic. And in particular, any compact class category is a Stautomus category where the two monadal structure will coincide. Another example of Stautomus category that is not compact clause is a category of finite dimensional Banach spaces and contractive linear map, or short linear map. So linear map is contractive if its norm is lesser than 1, which basically say that if you fed F with a subunit, something of norm lesser than 1, then you should get a subunit. So it's saying that F preserves subunits. And this is actually one of the original example of Stautomus category in Barr's paper where he introduced the notion of Stautomus category. The only thing is that in this paper, he gives a slightly different definition of Stautomus category, where he doesn't talk about par, so he doesn't talk about disjunction, but just about the tensor and the negation. And this is a shame because if you look at the norm for the par, the norm for the disjunction, it's the so-called injective cross norm, which is well known in functional analysis, and the tensor is a projective cross norm. And so they are known because they have nice property, one of which is to say that any norm that you can put on the tensor project will fit just inside, between those two norms. So they are extremal among all the norms that you can put on the tensor project. And so when you look at the definition of these two norms, it's not obvious that this thing will be a Stautomus category. And it's not obvious either why this Stautomus structure connect with the property of this norm being extremal. So trying to understand that was one of the motivation behind our work. And so to do that, we go from categories to polycategories. And this builds on old ideas. First one by Lambeck, where he had the idea of interpreted intuitionistic sequent calculus using multicategories. So multicategories are analogous to categories, except that your domain is a list of objects. So you can have multiple inputs. And one of the main points of multicategories is that in a multicategory, the connective interpreted as a universal property instead of asking for some monadal structure or asking for some structure on a category. And this can be extended by replacing multicategories by polycategories. So where now polymaps also have multiple outputs. This has been done by Chabot, which was one of Lambeck's students, to model classical sequent calculus. And later on in the 90s, Coquette and Seeley studied multiplicative linear logic using that, and what they called two-tensor polycategory with duals, and that we will call a representable polycategory with duals. So the point is the same as for multicategories. So representable polycategory with duals are equivalent to Stauten-Muth category, except that all the connective are given by universal property instead of asking for some modal structure. Another line of work that inspired this paper is the work by Leda about fibration of multicategories. So he observed in the early noughties that there is analogies between multicategories and fibered category. And he made this connection precise by introducing the notion of fibration of multicategory, and more particularly of covariant fibration of multicategory or up-fibration of multicategory. And he proved that modal categories are just a special case of multicategory, of fibration of multicategory. So this gives still another way of thinking of models of linear logic. Now, so the first way was as some structure on a category. The second way was as some universal property in a multicategory. And now we can also think of those as being some fibrational property on your multicategory. This has been extended to a contravariant fibration and to bifibration of multicategories, and for example, used in a paper by Licata, Schulman, and Riley. And this is closely related to a monadal clause category. So in our paper, there are three main contributions. The first one is to introduce a notion of universal polymap. And the idea is that this will encompass all the universal property of the connective. So it's a general notion of universal polymap, such that the tensor, the par, and the negation will all be a special case. A second contribution is this notion of bifibration of polycategories. And we will see that Cartesian polymap generalize in some sense universal polymap. And in particular, that Stauten-Muth category can be understood using some fibrational properties in your polycategory. And the last contribution is a polycategorical Grothendieck correspondence, because of course, if you talk about fibration, at some point you need to mention Grothendieck construction. So what we did is to construct a Grothendieck correspondence for polycategories. And using that, we get back a recent observation by Max Schulman that Stauten-Muth categories can be understood as a Frobenius pseudomonoid in the two polycategory of multivariable adjunction. And we'll see that this thing can be linked to the fact that there are some special fibration of polycategories. Okay, so let's go into the definition. And instead of going through the definition, I will just give you a diagram that explains the composition. So as I said, in polycategories, you have polymaps where you have multiple inputs and multiple outputs. So our diagram will be drawn from left to right. And there is some important things to understand about the composition. And the first one is that composition happens along a specific object, and just one. So you cannot compose along multiple objects at the same time. So this makes polycategories different from polymaps or props. The second thing is about those crossing. And there is basically two notions of polycategories that you can take. One that is symmetric polycategory, in which case the crossing will be understood as some symmetries, or non-symmetric or planar polycategories, in which case you don't have symmetries, and so you cannot have any crossing. And this will impose a condition on your composition that you can compose only if, so for example, this is empty or this is empty, and only if this list is empty or this list is empty. So in order to have no crossing. So in this talk, I won't really talk about this difference because everything that we did on the paper work in both settings with just a slight modification. And of course, the composition will be unital with respect to identities. It will be associative, and it will also have the interchange law that say that if I have a polymap H and I'm trying to feed it two different polymaps, so on two different inputs, it shouldn't matter in which way I'm doing it. There is, of course, something similar for outputs. So if you think, for example, if you take this H to be something that takes two inputs and give you the tensor product of these inputs, it's just the interchange law for modal structure. It's just saying that composing, that taking the parallel composition, the tensor of f and g, could be done in any order. So some examples of polycategories. First, the terminal polycategory. This will be really important in the theory. And it has only one object that we will call star. And for each pair of arities, for each m and n, it has a unique polymap that goes from m copy of the star into n copy of the star. Then any star-autonomous category, or more generally any linearly distributive category, if you know what that means, will give rise to a polycategory where the polymap are taken to be a map from the tensor into the tensor product of outputs. So this is really similar to sequent calculus and to logic, where sequent with multiple hypotheses and multiple conclusions can be understood as taking the conjunction of the hypothesis and the disjunction of the conclusion. In particular, any modal category or any compact clause category will give rise to a polycategory where polymaps goes from the tensor of the inputs into the tensor of the outputs. So from that, we can deduce that there is a polycategory of Banach spaces and contractive maps, but we don't want to use the star-autonomous structure of F-ban to define the polycategory, because the main point of this work will be to say that this star-autonomous category can be actually deduced from the polycategorical structure. And so we want to define the polycategory without making any reference to tensor par. And so to do that, we introduce the notion of contractive polylinear map. So a polylinear map is just a map that goes from from the tensor product of the inputs into the tensor product of the outputs, and it's contractive if this holds. So let me just say that. So rho will be a list of states, and you can think of state as element that you will feed f. And the pi will be a list of effect, and you can think of this effect or functionals as being things that you will probe f, the output of f. So this saying that the norm of lesser than 1 is just saying that rho is unital or subunital, exactly. And so this norm lesser than 1, so for the effect will in some sense test for subunitality. So if you feed an effect with something with a subunit, it will give you something that a scalar that is a subunit. And so basically, this contractivity definition really means that f respects subunitality. So it means that if you feed f with subunits, the result will be subunits. And I wanted to present this in this way because we can see that thinking of vector spaces as some systems system and processes, then putting a norm on them is really specifying some property, so this subunitality property. And so we start with a compact clause category of system and get a star-autonomous category, or now a polycategory, that represents some property of your systems. And so all the things that we'll be doing there for Banach space, you can do for other examples of properties. And one example comes from the work by Alex Kissinger and Sander Wellen, where they talk about causal structure. And so they start with some system, and then they impose to them the property of being causal for the states. And so all the things that we'll be doing can also be done in this example. And yeah, I'm working right now on trying to generalize that and be able to talk about other properties of system using this kind of settings. So let's go back a little to the theory. And as I said before, what is interesting with polycategory is that you can express tensor, pairs, and duals as being some universal objects. So you do that by asking, for example, for the tensor, asking for the existence of a map like that goes from AB into A tensor B, that will have some universal property that I won't go into the detailing of. The pair will come with a map that goes out of the pair into AB, and the dual will come with cup and caps. And all of this can be understood using the same notion of universal map. And a polycategory that has all tensor, pairs, and duals will be called a representable polycategory of duals, and it is equivalent to a star autonomous category. So of course, our example of Banach spaces is actually a representable polycategory of duals since it's come from a star autonomous category. So this universality, this notion of universal polymap that encompass the tensor, pair, and negation is given by this diagram. And so it will be a universality on a specific input or a specific output. So for example, U is said to be universal in A if this factorization property holds. So any H that could be a factor of U through A will actually be a factor. So you can find something to a factor H through U, and this should be unique. And it's the same for an input. So if H could be factor through N for this input, then I will be able to produce a polymap that make H such a factorization, and this polymap will be unique. And so a polycategory will be said to be star representable if it has all universal objects. So what I mean by that is that if you are specifying all of the type of the polymap except for one, I can produce this object and a polymap that will be universal in this object. And so this can be for an input or an output. And so using that, we can specify, we can actually get tensor, pair, and negation as being some universal object. And we can prove that any universal object can be built from this connective. And so in particular, this notion of star representable polycategory is equivalent to the notion of representable polycategory of duals. So now I want to talk to you about bifibration of polycategories, and we will see how this generalize representable polycategories, star representable polycategories. First, let me just give some terminology, and we will call any functor of polycategory a poly-refinement system. And so this terminology is inspired from the study of type refinement system. We will draw poly-refinement system vertically, where the top part will be in the domain, the bottom part in the codomain, and we'll take object and polymap to lie directly above their image. So for example, this specific graph, this specific image, say that composition is preserved, because it's saying that the composition is sent to the composition of the image. Using this graphical notation, we can express the definition of Cartesian polymap easily. And so if for a minute you just forget about this line and just look at the line on top, it's exactly the same definition as universal polymap. So the difference is that this factorization will actually be parameterized by some base category. And so this factorization should happen. So we will ask for this factorization to exist only if it's already existing in the base category. And so in particular, if the base category doesn't have any information, so if all of these things doesn't hold any information, we will just get back the notion of universal polymap. And so this means that if you take B to be the terminal polycategory, so in the terminal polycategory, the composition will always exist and it will be unique. So this doesn't give any new information. Then a Cartesian polymap over 1 will be the same as a universal polymap. with this notion of Cartesian polymap, we can talk about Cartesian lifting or pullbacks. And so to do that, we start with a polymap in the base, so in the codomain, and we give types that lies over all the type of F except for one input. So everything is specified except from one input. And what we want is to find something that lies over this input that comes with a polymap that will be Cartesian and that will lies over F. And so this thing will be called the pullback, so the pullback of sigma along F in context pi. And this map will be called the Cartesian lifting of F. Of course, there is something similar for outputs, where you will get the push forward along a map. And then a bifibration will be something that has all Cartesian lifting. So all pullbacks and push forward exist in bifibration. And as I said before, when I was showing you the drawing on explaining Cartesian polymap, if the base category doesn't hold any information, so if it's the terminal polycategory, then this will be equivalent to the notion of star representable polycategory. And so in particular, we'll get that any star autonomous category can be thought of just a polycategory that is bifibered over the terminal polycategory. So this is what we want to use to understand the star autonomous structure of F-ban. Because the idea is that if I have a functor, so a polyreference system like that, so first assume that this is a bifibration, and B is star autonomous or star representable. So this means that the functor from B into 1 is also a bifibration. And since bifibration compose, we'll get that the functor from E into 1 is a bifibration. And so this will give us the star autonomous structure on E for 3. But we don't really need for this to be a bifibration. We don't need all pullbacks and push forward. We just need some of them. And basically, this is because of this proposition that say that if I'm starting from a universal map in B, and I'm taking its Cartesian lifting, then the Cartesian lifting will be universal. And so the only Cartesian lifting that I need are the Cartesian lifting of universal polymap. And so, for example, I will get the tensor product in E by taking the push forward along the map that defines the tensor product in B. So to apply that to our example of Banach spaces, we need to understand what are pullbacks and push forward in this case. And so I'm starting with a polylinear map F, so a map from the tensor product of A's into the tensor product of the outputs. And I'm specifying norms for all the vector space except one input. And so what I want to get is a norm on this input that is a pullback. And so in particular, it should make F contractive, which means that if I'm taking any subunits, rho 1, rho 2, and pi, like that, and I'm building this effect, so this effect should be contractive. So it should verify this effect should probe for subunitality of things. And so if I'm giving X subunital, this thing should be subunital. And so with this intuition, we can define the norm on AK to be just taking this value for all subunits. So we take the sub for all subunits. And so if this thing is subunital, so if this thing is lesser than 1, then all of this scala will be lesser than 1. However, this doesn't define a norm in general. This just defines a pseudonorm. So a pseudonorm is like a norm, except that you can have multiple vectors that have norm 0. But we can characterize map F such that this thing is a norm, and we will call them injective in AK. I won't get into the definition. But in this case, so when this is actually a norm, this defines a pullback. And instead of looking at Banach spaces, we could look at a pseudonorm space. And in this case, all pullback will exist. Now for the push forward, so I'm starting with the same thing. I have F that is a polylinear map. I have norm on all the vector space except one output. And I want to put a norm on this output that makes F contractive, and that is a push forward. And so first, let's start with taking a Y in BK that has this form. So basically, that is in the image of F. In this case, I want the norm of Y to be just the product of the norm of the inputs and outputs. And the reason for that is that if these things are subunits, so if the norm is lesser than 1, then their product will be lesser than 1, and this will make Y a subunit. Then, if I'm taking any linear combination, so if I'm taking Y to be a linear combination of things in the image, then I'm just taking the sum of all the norms. But finally, Y could be decomposed in such a linear combination in different ways. So this decomposition need not be unique. So I'm taking the nth on the infimum on all the decomposition possible. And this will define my norm on Y. But once again, it's not really a norm, it's an extended norm, which means that it can have infinite value. And this is just because this decomposition doesn't necessarily exist. And if it doesn't exist, the infimum will be infinite. But if F is what we call surjective, which means really that for any Y, this decomposition exists, then this will define a norm, and it will be a push forward. So of course, I could extend everything to extended norm or extended pseudonorm. And in the case of extending the pseudonorm, then I will get a bifibration. But I don't really need that because the thing that matters to me, so the map for the tensor and for the dual are surjective and injective. So the pullback will exist for the tensor project, the push forward, the push forward will exist for the tensor project, the pullback will exist for the par. And this gives us a way to lift the compacted structure of F vect into a star-term structure on F ban 1. And the property that I talked about at the beginning, saying that this norm that we get in this way are extremal, come really from the universal property, from the factorization property, the Cartesian map. So the fact that the norm for the tensor is the biggest norm really comes from the fact that the tensor is a push forward, and the fact that the one for the norm for the par is the smallest one comes from the fact that it is a pullback. So let's just really briefly about the Grothendieck correspondence, mainly for people that already know about Grothendieck construction. So first, we have what we call the Grothendieck-Benabou correspondence that goes from functors of polycategories, so between functors of polycategories, and lax normal functors into dist, where dist is a two polycategory of distributors or profunctors. This can be specialized to bifibration by looking at pseudo-functors into the two polycategory of multivariable adjunction. And if we take B to be 1, so to be the terminal polycategory, we will get correspondence between bifibration over 1 and pseudo-functor from 1 into a multivariable adjunction. And so we know that this thing is a star-term category, and this pseudo-functor really give a Frobenius pseudomonoid in multivariable adjunction. And so this relates to the fact that Schumann expressed that I talked to you about in the beginning of the talk. And just this can be a little bit made a little bit more general by saying that if I'm starting from any Frobenius monoid in B, then I will get a Frobenius pseudomonoid there. And so that will make a star-term structure on the fiber over my Frobenius monoid. So this means that if I am bifibered and I look at the fiber of a Frobenius monoid, then this will have a star-term structure. So let me just talk briefly about some future work that we will be looking at. So the first one is to find new examples of polycategorical bifibration, and in particular of this idea of looking at some properties of systems. And so this relates to this second point, where I want the base polycategory to be compact clause, so to represent system. And I want to understand in this case if there is anything new that you get. So for example, the example of Banach space and also the example of causal system, both have more structure than just being merely a startmost category. They also have things that we call the mix map. They also have that any first order system, for first order system, if you take the tensor product and the par, they are the same. So the tensor product and the par are different just for higher order systems. And I want to understand if this thing come from, so if it can be understood in this setting. Then I want to relate that to the notion of refinement system. And finally, I would also want to understand other notion of fibration. So where the Grothendieck correspondence doesn't go into profunctors, into distributors, but go, for example, into the two polycategory of relation or the two polycategory of bimodules. And see what kind of fibration you get. So for example, for relation, I think you will get some notion of discrete fibration. And finally, we'll be interested also in looking at polarized model of polarized logic using this. Okay, so let me conclude there and just give you a summary table of the different way of thinking about model of multiplicative linear logic. So either as a startmost structure, where everything is given by a structure, by representable polycategory, where everything is given by universal object, by fibered polycategory, where things are given by Cartesian map, so by fibrational property, or as Frobenius pseudomonoid in a multivariable adjunction. Thank you.
Thank you very much, Nicolas. Thank you. Either by unmuting and clapping or by emoticons, whatever is easier for anyone. So there are no questions on the chat as far as I could see. I'll check the raised hands, but if anyone has any questions, feel free to now unmute and ask the questions to Nicolas. Yes?
Yeah.
Yes, go on.
I hope this question is meaningful. Could you comment on the possible significance or relationship of this work, as it relates to the notion of fixed point theorems and the whole idea of Banach spaces and solutions based on contraction maps? I assume that there's a connection, or am I missing a point?
Okay, so to be honest, I'm not really familiar with this line of work. So because in this example, everything is really easy because we are looking at finite dimensional Banach spaces. So you don't have any of the meat that you have in infinite Banach spaces. So this can be a little generalized to that, but yeah, I don't really, I'm not really familiar with the fixed point theorem that you were talking about and how it is used. So, but yeah, I would be glad to talk about it afterwards and to see if there can be any relation.
Yeah, because the notion of contraction map and Banach spaces, is widespread because of its relevance to fixed point solutions of transformations. So I thought there might be some analogy.
Okay, so yeah, I will be glad to take a look at that and maybe I'll get back to you later on this.
Thanks.
Any other questions or clarifications?
I guess I could ask about if you have, so for the sequent calculus with ands on the left and ors on the right, what might is there a way to say what your results could mean in that context? Or
you mean
if I have, let's say I have a functor between two different logical systems in that setting as polycategories, does that make sense?
Yes. So So one thing that we want to look at is, so this notion of fibration, and especially fibration of monadal closed categories, has been used to talk about refinement types, or subtyping if you want. So the idea of a refinement type is that you start with a type system, and for each type you assign a property that is represented by a set. And this can be analyzed using fibration of categories, of monadal closed category. And so we hope that this could be extended to this setting. And so to start with some logic, or for example, yeah, to start with a system that is represented by a second calculus, and to refine it, and to represent this refinement by a bifibration of polycategories. Mm. Does this answer your question?
Well, it probably answers a better question than the one I asked, but I was just, I mean, I could leave it for other people. I don't know if there are other questions. I was just wondering, does a map of logical theories give rise to a functor between the polycategories of sequence between them, and if so, what kind of map between between theories? I guess it would have to preserve various things. I don't know what. If it has to be like a regular functor, or I don't know. Yeah, sorry, a coherent functor. What sort of map between logical theories would give rise to a map of their polycategories, and what the fibrations would mean there?
Yeah, so I'm not sure to be honest. So yeah, this is something to be checked.
Okay.
So I haven't really thought of it before. So.
Okay. Are there any other questions? Otherwise, we could thank the speaker again